Okay, so in the previous lecture, I started discussing about sorry, electrophilic aromatic substitution. No? And there are 5 basic reactions: nitration, sulfonation, halogenation, Friedel-Crafts alkylation, and Friedel-Crafts acylation. Okay, and the corresponding electrophiles are NO2 plus, sulfonium ion, Cl plus, and Br plus, alkyl carbonium ion, and acyl carbonium ion. Okay. Of all these reactions, the sulfonation reaction is quite unique because this is the only reaction that is reversible. Okay. So you know what is the reversibility concept? No, it's based on thermodynamics. No, the higher the temperature, okay, the greater the possibility for the reaction to pass through the barrier. No? So in electrophilic aromatic substitution, the product yields are kinetic controlled. No? So meaning the lower the activation energy, the faster the rate. No? Now in sulfonation process, since the reaction is reversible, after the product is formed, no? In sulfonation, you react this with fuming sulfuric acid, which is a mixture of sulfur trioxide and sulfuric acid. Now, if you use this mixture, you have benzene sulfonic acid. Okay? But then if you heat the substance at 100 degrees Celsius, the electrophile will be dislodged from the benzene. So you will end up with benzene again. So that's why doing this reaction should be done at lower temperature so that you will produce the benzene sulfonic acid. Now, if you talking about electrophilic aromatic substitution, okay, now we look at the activity. We say activity, how reactive is the benzene ring, and the orientation of the electrophiles. If there are more than one electrophile that will be attached to the benzene ring, okay? After the first electrophile is attached, will the second electrophile be at the ortho, meta, or para position? So that's the question. It will depend on the first substituent attached. Is the substituent electron donating or is it electron withdrawing? Okay. Talking about reactivity of the benzene ring, the presence of electron donating group will increase the reactivity of the benzene ring. You know why? Because the intermediate in this reaction is a carbonium ion. And carbonium ion can be stabilized by electron donating group. So this will lower the activation energy, the barrier of reaction, right? The lower the activation energy, the faster the rate. Electron donating groups can stabilize the intermediate and therefore enhances the rate of reaction. On the other hand, electron withdrawing destabilizes, no? Because they withdraw electrons, they make the positive more positive. And this will raise the activation energy, therefore decreasing the rate. So if we compare the reactivity of benzene with electron donating group, benzene without any group attached, and benzene with electron withdrawing, the most reactive would be benzene with electron donating because it will lower the activation energy due to the stability of the carbonium ion. So that's why you have that trend. And we can classify electron donating and electron withdrawing based on their ability to donate. Okay? For electron donating, we can classify them as strongly activating, moderately activating, or weakly activating. So in the strongly activating category, you have the amino group, the methylamine group, the hydroxyl group, and methoxy group. And you notice electron donating groups, they have lone pair to donate to the benzene ring. Okay? And within this category, we can even differentiate their ability to donate. For example, here, if you compare which one is more electron donating, is it the amino group or the hydroxyl group? The amino group will be more electron donating. You know why? Because the nitrogen is less electronegative than oxygen. So therefore, nitrogen can easily donate its lone pair to the ring. So that's why it is more electron donating. Okay? Now, for the moderately activating, this include the amide group and the ester group. And you notice again, you have the lone pair, no? In nitrogen and oxygen that will be donated to the ring as indicated by this arrow here. But why is it only moderately, not strongly? Because at the back of the nitrogen, there is this group, the carbonyl group, which is electron withdrawing. Look at the lone pair. The lone pair can also delocalize towards the carbonyl. And that is not good for the lone pair to be donating its electron density to the ring if there is a competition. The same thing here with oxygen, there is a competition that will weaken the ability of the nitrogen and oxygen to donate. So that's why they are classified as moderately activating. The third category or group, which are weakly activating, would include the methyl, another aromatic group, or even alkene. And you know why they are only weakly? Because they don't have lone pairs. So what electron pairs are they donating? Well, for the methyl, you have the sigma bond. For aromatic, you have the pi bond. And for alkene, you have the pi bond. So all the electrons here are in a bond. Unlike there, in moderately and strongly, they are lone pairs. They are not in a bond. So therefore, they can easily be donated. Okay? Now, for the electron withdrawing groups, of course, we don't expect a lone pair. Oh? So for strongly deactivating, you call that electron withdrawing are deactivating groups. This include the NO2 and the nitrogen in its ammonium state, no? Meaning salt form. You have the nitrogen there, but 4 groups are attached. So there is no lone pair anymore. And that becomes a very strong electron withdrawing group. Similarly, the cyanide is also classified as strongly deactivating because although there's a pi bond there, but carbon here is partially positive. And remember the orbital electronegativity of sp, because this is sp hybridized. Its S character is 50%, so it becomes electron withdrawing rather than donating. The same thing with sulfonium ion and carbon with 3 halogens. You know, halogens are electron withdrawing by inductive effect. Okay? So that becomes, the carbon becomes very positive because you have 3 electron withdrawing group, and therefore it is also a strongly deactivating group. Now for moderately, look at that. This include the aldehydes, the ketones, the ester, the carboxylic acid. The carbon there are partially positive. So they are also electron withdrawing, moderately deactivating. Okay? For weakly deactivating, these are the halogens. Right? They are electronegative, so they withdraw electrons. No? But why they are classified as weakly deactivating? Because the halogens have lone pairs class. No? So they can donate electrons to the benzene ring by resonance, but they can also withdraw electron from the benzene ring by inductive. And we said, when we discussed structural effects, we said that for halogens, the dominant structural effect is inductive. So that's why they are classified as electron withdrawing rather than electron donating. Now, there is a very important point here when it comes to orientation. Because generally, for electron donating groups, when they donate electrons to the benzene ring, the carbon positions that will accept that electrons from these substituents will be the ortho and para positions. So these are the carbon in the benzene ring that will have higher electron density. So therefore, the electrophile will be anchored at the ortho and para positions. So that's why electron donating groups are called ortho-para director. So if the first substituent is electron donating, the next electrophile will be anchored at the ortho or para position. So that's why they are called, the first substituent is called ortho-para director. For electron withdrawing groups, they withdraw electrons at the ortho and para carbons. So therefore, the electron density at the ortho and para will be very low for electron withdrawing group. So therefore, the electrophile, if this is an electron withdrawing group, the electrophile will not be anchored at the ortho and para. It will be anchored at the meta position. So that's why electron withdrawing groups are called meta director, except, so there's an exception now, okay? Because the halogens are electron withdrawing, but they are not meta director. They are ortho para directors. Why? Because they have the lone pair. Okay? So during the reaction, they anchor the electrophile at the ortho and para, but overall, they will deactivate the benzene ring. So that's why they are still classified as electron withdrawing group rather than electron donating group. Okay, now, so based on those classifications, it is now easy for us to arrange the following aromatic compounds in terms of increasing reactivity, for example, to electrophilic aromatic substitutions. Because we know that electron donating are more reactive. So methyl is electron donating. Methoxy is electron donating. So they are more reactive to electrophilic aromatic substitution. While the aldehyde is an electron withdrawing, nitro is an electron withdrawing. So they are less reactive. So if we're going to arrange this, the lowest reactivity would be the electron withdrawing group. But there are two electron withdrawing group. Which one is most electron withdrawing? Of course, the nitro. So that is the least reactive, followed by 2. And then you have the benzene at the middle, followed by donating groups. We have 2 donating groups again, but methyl is less donating, so therefore less reactive than methoxy. So that's why you have these arrangements here. Okay. Now let's look at the side reactions. They say side reactions class. These are the reactions of the substituents that have been attached already to the benzene. For example, when you do Friedel-Crafts alkylation reaction using methyl chloride, your electrophile here is methyl carbonium ion, because the chlorine will be removed by the Lewis acid, right? So that's why you will end up with toluene as a product. Now, what are the possible reactions of methyl? Now, methyl is an alkane. And if you recall, alkanes undergo free radical substitution reaction. So if you react this with chlorine in the presence of UV light, then the hydrogen can be replaced by chlorine, generating chloromethylbenzene as the product, right? And we said in our discussion on alkane that all the hydrogens can actually be replaced. That's why in free radical substitution reaction of alkane, monohalogenated, dihalogenated, trihalogenated, etc., no, can be produced. So if you add chlorine in excess, right, all the hydrogens there will be replaced. So you will end up with trichloromethylbenzene. And you can see the change in the property of this products class. You see, your methyl is an orthopara director, right? Because it is an electron donating group. But here, you attach a chlorine, right? So the methyl group is still electron donating because there are 2 hydrogen. But if you compare methyl and chloromethyl, the methyl will be more electron donating. This one will be less because you have now an electron withdrawing chlorine. But it is still electron donating. So meaning, it is still an orthopara director. But look when all the hydrogens are replaced with chlorine. This group is classified as a very strong deactivating group, and it is a meta-director. So therefore, if you subject this benzene to another electrophilic aromatic, the next electrophile will not be at the ortho and para. It will be at the meta. But this one here, if you subject this, it will be at the ortho para. This one also will be at the ortho para, but less reactive than the methyl. Okay? Let's have other side reactions. Okay, look at this. Supposing you have ethyl benzene instead of methyl benzene. If you add an oxidizing agent like potassium permanganate, it will always produce benzoic acid. The same thing here. For methyl benzene, if you add an oxidizing agent, the methyl group will become carboxylic acid group. For ethyl, the same thing. What will happen to the other carbon? Because ethyl have 2 carbons. Well, the other carbon will become carbon dioxide. If this one is very long, you have a very long carbon chain there, the major product will always be this benzoic acid, and the rest will become carboxylic acid if there is a very long carbon chain. Okay? Now, supposing your substituent is ethylene. You have a double bond there. There is an alkene. And you know what are the possible reactions of alkenes, right? We have discussed that thoroughly. It can undergo hydrogenation reaction. In the presence of platinum, for example, then you produce ethyl benzene. If you add hydrogen chloride, then your alkene will undergo hydrohallucination reaction. And following Markovnikov's rule, the hydrogen will go to the carbon with more hydrogen, and the chlorine will be here. So you will end up with this product. Okay, chloroethyl benzene. You can even do the hydration process in the presence of sulfuric acid catalyst. So this one again follows Markovnikov's rule. So you have the alcohol product. Now, if you want to generate the alkene, well, you have to remove the hydrochloric acid here in this product. So how is the hydrochloric acid removed here? Well, you have to add a base if you want to remove the HCl. Example of a base, organic base, would be tertiary butoxide. In the presence of its conjugate acid, tertiary butyl alcohol. This is how we condense the name, no? T for tertiary, and then you have potassium butoxide. Okay? This is a very strong base, and this will remove the HCl plus. That's why you can regenerate the styrene. Okay? And this product is the precursor for the synthesis of styrofoam, no? Mga styrofoam cups, no? Polystyrene. How about the second reaction? If you want to remove water, of course, you cannot use base to remove water. You have to use a dehydrating agent. And one of the dehydrating agents would be concentrated sulfuric acid. You heat that, the water will be removed, and you can recover the styrene again. Okay? Now, so, halogenation of the methyl group using UV light is very difficult to control because you will end up with monohalogenated, dihalogenated, etc. But there is a particular reaction that we discussed in reaction of alkane to generate only one or to produce only one replacement of hydrogen. And that is through the use of NBS, no? Or N-bromo succinimide in the presence of UV. So if you use N-bromo, there is no multi-replacement of hydrogen, only one. So that's why you will end up with bromo-methylbenzene. How about if you have ethyl benzene and you use NBS? Now, since only one hydrogen will be replaced, which hydrogen? Is it the hydrogen from the methyl or is it the hydrogen from the methylene? Okay? Now, that can be answered if you know the intermediate for free radical. The intermediate for free radical is a radical intermediate, and we classify radical as primary, secondary, or tertiary. So if the hydrogen is removed here from the methyl, the radical that is formed is primary. But if the hydrogen is removed from the methylene, the radical is secondary. And since secondary is more stable than primary, then the hydrogen that will be replaced will be from the methylene. So you will end up with this replacement and product. Okay. Now let's look at the orientation. Okay. So for example here, you have this series of reactions. So halogenation of benzene in the presence of ferric chloride will produce chloropenzene. So you have the first substituent, chlorine. Now, chlorine is a deactivating group, but ortho-para director, no? Kasi exception yan. So if you subject this chlorobenzene to nitration reaction, which utilizes these reagents, the electrophile here is NO2+. And since chlorine is an ortho-para director, then you will have two products, one at the ortho, another one at the para. And which one do you think will be greater in terms of yield? Is it the ortho or para? Well, if there is not much of a steric effect. Now, since the ortho has two positions, para has only one position, then you will have more of the ortho product. That is if there is no steric effect. Okay. But if there is steric effect, for example here, if you subject benzene to Friedel-Crafts alkylation reaction, you produce toluene. Now, methyl group is an activating group, so therefore this is an ortho-para director again. So if you subject this to nitration, you have two products again. But since methyl is not really a bulky group, again, the ortho will have a greater yield compared to the para. But if you have this kind of reaction class, this is tertiary butyl chloride. You react this with ferric chloride. Okay, the chlorine will be removed by the Lewis acid, so the carbonium will be here at the carbon. So this is the one that will be attached. So you have tertiary butyl benzene. Now, if you subject this to nitration reaction, obviously, there is a steric effect that's too big. So the NO2 will not be at the ortho, but rather at the para position. So this becomes the major product. Okay? Now, in halogenation reaction class, you notice I added the Lewis acid ferric chloride. But in actual laboratory setting, the ferric chloride is not added directly. What is added is chlorine and Fe. Because if you add these two reagents, iron and chlorine will produce the ferric chloride. So you produce the ferric chloride in situ. You call that in situ. Right there. You are not adding it as ferric chloride. Why? Because ferric chloride is very sensitive to moisture. It will easily react with water to form ferric hydroxide, and we don't want that to happen, right? So that's why the ferric chloride is usually produced by mixing iron and chlorine, the test tube, to produce the ferric chloride. Okay. Now, so here, okay, if we talk about orientation now, look at this example. You have the nitration process generating nitrobenzene. And this is followed by another type of electrophilic aromatic substitution halogenation reaction. You will only produce one product because nitro is an electron withdrawing group, and therefore it is a meta director. So that's why the Cl plus here is attached at the meta position. So you will end up with that product. Now, supposing you have two substituents, and then you still subject that to another electrophilic aromatic substitution, okay? So I'm just placing here E+, So you can use any of that, So the question now is, where would be the attachment of the third electrophile? Well, it will depend on the two substituents. Which one is more electron donating will control the orientation. Now, if we compare chlorine and methoxy group, okay, the methoxy group is more electron donating than chlorine. So therefore, the electrophile, since methoxy is ortho-para director, then the electrophile will be anchored ortho to the methoxy. And these are the ortho positions to the methoxy. So this electrophile will be attached here, okay? Not here, because below is the ortho to the chlorine. Okay, but above is the ortho to the methoxy. So there are supposed to be two products here, ortho and para, but the para is already occupied by the halogen, so you will end up with only the ortho product. Okay? Okay, now let's go to synthesis. Okay? Now, supposing you have the benzene here and your target product is this 3-chloro benzene sulfonic acid. Okay? How are you going to synthesize this from benzene? Now, since there are two substituents attached, so your benzene will undergo 2 rounds of electrophilic aromatic substitution. So the question now is, which one will be attached first? The chlorine, followed by sulfonic acid group, or the sulfonic acid group followed by chlorine? Okay, here's the trial. If you attach the chlorine first, by chlorination reaction, you produce chlorobenzene. And take note that chlorine is an ortho-para director. So if this is followed by sulfonation reaction, then the sulfonic acid group will be attached at the ortho position like this, and at the para position like this. And if you notice, these two products are not the target product. Look at the target product. It's meta. Okay? The sulfonic acid group should be at the meta position. But here, the sulfonic is at the para and ortho. So you made a mistake in the sequence. So the best sequence would be sulfonation first. Okay? So when you do sulfonation, you have benzene sulfonic acid. And sulfonic acid group is an electron withdrawing group, a strongly deactivating group. And you know what are electron withdrawing groups? They are meta directors. So therefore, it will direct the chlorine electrophile at the meta position. That's why you have this as the target product. Okay? Now, in our second example, you have benzene converted to, your target is para-ethyl. This is ethyl toluene. Okay? So the question, there are two substituents again. Which group will be attached first? Is it ethyl? Or is it methyl? Or is it ethyl first? Well, either of the two substituents. You know why? Because both are orthopara directors. Ethyl is orthopara director because it is electron donating. Methyl is also orthopara director because it is electron donating. So, for example here, if you do alkylation first to attach the methyl, followed by second alkylation using ethyl, you produce this target product because methyl is an orthopara director. And this is at the para position. Now, if you do ethyl first, Friedel-Crafts ethylation, you produce the ethyl benzene, but this is also orthopara director. So when you do the methylation, the methyl will be at the para position. So that's why either way is possible. Okay, now look at this third challenging reaction. You have benzene, okay, converted to para-nitrobenzoic acid. Okay. Although there are two substituents only here, look at that, you only have two substituents, the benzoic and the nitro. But unlike the two examples, you have a problem with carboxylic acid because you cannot attach this directly. There are only 5 basic electrophilic aromatic: alkylation, nitration, sulfonation, Friedel-Crafts acylation, and halogenation. No problem with nitro because you have nitration. You can attach this one to the benzene directly. But there is no reagent for carboxylic acid group to be attached directly. So in other words, it gives you the hint that this one is coming from side reactions. And what is that side reactions? Well, here. This benzoic carboxylic acid group comes from methyl. Because if methyl can be oxidized, if you add potassium permanganate, that methyl can be oxidized to benzoic acid. And methyl can be attached directly by Friedel-Crafts alkylation reaction. So therefore, this reaction involves 3 steps. Okay? So the question now is, what is the first step? Okay? What is the second step? And what is the third step? Okay, here. Now, since benzoic acid comes from methyl, and since methyl can be attached directly, then you have to use this reaction here because you can do Friedel-Crafts methylation reaction. So let's see. So in the presence of aluminum chloride, you have toluene. Okay, now, the second step is crucial because there are 2 possibilities, okay, for the attachment of the nitro. You decide to do methylation, okay? For the nitration, there are 2 pathways. Either you oxidize it with cheminophore first before you do the nitration, or you nitrate first before you oxidize. Okay? And you can see the difference in the reaction here. Look at the first one. If you decided to oxidize the methyl to form benzoic acid and do the nitration, that path is wrong. Why wrong? Because carboxylic acid is an electron withdrawing group. And since it is an electron withdrawing group, it is a meta director. So that's why when you do the nitration, the NO2 is attached at the meta. That is not our target. Look at that. Our target, the nitro, is at the para to carboxylic acid, not meta to carboxylic acid. So this is a wrong path. So what is the right path? Here. You nitrate it first. Because methyl is an orthopara director, then when you nitrate, the NO2 will be at the para. Okay? It can also be at the ortho. At least one of the products is para, so that's fine. And then you oxidize. So when you oxidize this one, then you have now the target product. Okay? So there. Now, analyze this one here. You have this structure with 2 benzene rings separated by an ester group. So the question, if this compound will undergo nitration, which benzene ring will be attacked? Is it the left benzene or the right benzene? Well, if you analyze the structure, you have to look for the benzene that is more reactive. Okay? And the more reactive here is the left, not the right. Why? Look at the oxygen here. The oxygen has a lone pair. And this lone pair can be donated to the left benzene. Look at the right benzene. The group here is carbonyl, which is partially positive. There is no lone pair here. So this is electron withdrawing. And this will lower the activity of the right benzene. But the left benzene, okay, has a donating group. Okay? So this will be more reactive. Now, the second question is, where are you going to attach the electrophile NO2+? At the ortho of the left benzene, meta, or para? Now, since electron donating is ortho-para director, then you have to attach the electrophile either at the ortho or para position. So that's why you have these two products where you have the NO2 at the ortho and you have the NO2 at the para positions. Okay? Now, let's look at a little closer with these reactions, the Friedel-Crafts reactions. And there are two Friedel-Crafts reactions, alkylation and acylation reactions. Okay? So, if you recall, in alkylation reaction, the electrophile that is attached is carbonium ion. And you have to be very careful with this because if you recall, in our discussion on electrophilic addition reaction, if the intermediate is a carbonium ion class, there is a possibility for it to undergo what? Rearrangement, no? Hydride shift or methide shift. Okay, so that will happen if you have carbonium ion intermediate. Okay, and in Friedel-Crafts reaction, your electrophile is carbonium ion. So if you subject this to methylation reaction, your carbonium ion here is methyl. And no problem with that one because methyl has no tendency to rearrange. Then you produce the toluene product neatly. Now, what will happen if you have this kind of alkyl halide, propyl chloride, and you subject this to a Friedel-Crafts alkylation reaction? Well, the chlorine will be removed by the Lewis acid. So the carbonium will be here. And this is the one that will be attached to the benzene. So you are expecting this product, propylbenzene. However, this is not the product. You will get this product class, isopropyl benzene. Why this product? What happens? Okay, this is what happened. When the chlorine is removed by the Lewis acid, you generate a primary carbonium ion, but this will undergo hydride shift. When the hydrogen moves here, it generates a more stable carbonium, the secondary. And this is the one that will be added to the benzene. That's why you will end up with isopropyl benzene. Okay? Now, supposing you want this product, propyl benzene. Well, you cannot use this process because you will always end up with isopropyl benzene. So how do you produce this? Well, there's a way. You do Friedel-Crafts acylation reaction using propanoyl chloride. So the chlorine will be removed by the Lewis acid again. The positive will be here. And this is the one that will be attached to the benzene. So you will end up with a ketone. Okay? So there is still oxygen here. That is propyl. So to remove the oxygen, you subject this product to reduction process. Reduction is addition of hydrogen, removal of oxygen. And there are three possible reducing agents that you can use. One is an alloy or an amalgam of zinc and mercury in the presence of hydrochloric acid. You know, metal reacts with acid to produce what? Hydrogen gas. And that hydrogen can displace the oxygen to produce the propyl benzene. And you call this reduction Clemmensen reduction. Okay? Now, another reducing agent utilizes hydrazine. This is the structure of hydrazine under basic condition. So the oxygen will also be replaced by hydrogen to produce propyl benzene. And you call this reduction process Wolff-Kishner reduction. The third type of reducing agent is very simple. You just use hydrogen gas in the presence of palladium and powdered carbon, activated carbon. So this will also remove the oxygen to produce the target product without rearrangement. Okay, now for Friedel-Crafts acylation reaction, okay, this is the process of producing aromatic ketone. Look at this. This is a ketone with a benzene ring. You call this acetophenone. So if you use acetyl chloride, again, the chlorine will be removed by the Lewis acid, and this carbon plus will be attached. So you have acetophenone. Acetophenone can also be synthesized using acetic anhydride. So this is the structure of acetic anhydride plus. If you add the Lewis acid again, this one will be cleaved, and this acetyl group will be attached again, and except that there is a byproduct, acetate, coming from acetic anhydride. Okay, now, there are certain limitations of the Friedel-Crafts reactions plus. Now, what are these? You know, of all those reactions that we discussed, okay, the Friedel-Crafts reaction class is the slowest reaction, okay? So that's why if there are electron withdrawing groups attached to the benzene ring and you subject this to Friedel-Crafts alkylation or Friedel-Crafts acylation, there will be no reaction class, no reaction, as long as there is an electron withdrawing group here. For example, here, you have nitrobenzene. You subject this to a Friedel-Crafts methylation reaction. And NO2 is a meta director, right? Because it is an electron withdrawing group. So you are expecting this product, methyl, attached at the meta position. But this can never happen. You cannot produce this product because NO2 is an electron withdrawing group. So there will be no reaction. Okay? So, for other reactions class, like for example, if benzene has strong electron donating groups like OH and amino group, these are strongly activating groups, right, in our classification. If you subject these two compounds to electrophilic aromatic substitution class like bromination, you don't need to use a Lewis acid. Reaction can still happen. Like you just use bromine, it will produce the ortho and the para because OH is an ortho-para director. Similarly, if you have aniline, you have amino group. If you subject this to bromination, even without the Lewis acid, you will produce the ortho and the para also. However, this is an advantage class, no? But a disadvantage for aniline if you add a Lewis acid. Why a disadvantage when you add the catalyst? Okay, here. Amines are basic compounds, right? They are basic compounds. And they react with acids. Ferric chloride is an acid, a Lewis acid. So what happens is that if you add the Lewis acid here, the lone pair of nitrogen will be used by iron because iron lacks an octet of electrons, right? You have only 3 bonds there. So to make it 4, it has to use the lone pair. So what will happen? Your nitrogen will become positively charged. So there is no lone pair to donate to the benzene ring. So if you add the ferric bromide, the amino group will become electron withdrawing rather than donating. So that's why when you add the bromine plus, if there is the Lewis acid, the bromine will be at the meta position, not at the para or ortho, because of the electron, because of the reaction of the amino with the Lewis acid. How about the phenol? Okay, if you add a Lewis acid here, will it happen? No, just like the amino? No, because OH is not a basic. That's a hydroxyl group. It's not a basic group. In fact, it is acidic. Okay, so therefore, if you add the Lewis acid here, then the reaction will be enhanced. No, you will produce. If you add the Lewis acid for bromine class, all the ortho and para positions will be occupied by bromine. So you will have bromine here, you will have bromine on the other ortho, you also have bromine below. Okay, if you add the Lewis acid. So there, okay. So those are the important aspects of electrophilic aromatic. Okay, okay. So I think that's it, class. No,
Bye,
we're done
class.
with